Okay, I would like to thank the organizers inviting me and giving me the opportunity to make a short review of different kinetic methods applied in analytical chemistry. This presentation has been prepared with the help of Professor Ferreira from Brazil and Professor Piyaman Pansi from Thailand.
So could you please put it on slideshow mode?
Do you see me well?
Yes, thank you.
Okay. The idea is give a review of different kinds of analytical methods using kinetic methods, which can be applied both in the lab, can be applied some of them in situ, and also in process industrial applications. Well, we can apply kinetic method both for non-catalyzed reaction and also for catalyzed reaction. For non-catalyzed reaction, the rate of the reaction could be given by this equation, very well known, where K is the rate constant, which may be calculated from the Arrhenius equation. In this equation, we see that depends the constant from the temperature and the energy of the activator. We make the logarithm of this first equation, which can be applied to determine different kinds of products. In non-catalyzed reactions, usually we make the measurement of the product of the reaction. Since at the beginning we can consider that the concentration of A and B are almost constant, we have a variation, straight line variation of the product, and we can measure, we can represent the slope of this speed in front of the concentration of the product. You will have the calibration curve. Another way to apply the kinetic methods is making the measure the product a predefined time. We have the fixed time method. In the way we can represent the calibration curve, represent the variation of the signal in from the concentration. And finally, less used is to measure a predefined value of the signal and then represent the time in front of the concentration. These three methods can be applied both for non-catalytic and for catalytic reaction methods. Here, for example, we have a manual method to make the measurement of the concentration of the chrome in solutions. Chrome 6 is able to oxidize orthotoluidine, giving a blue compound, which can be measured at 330 nanometers. Here we have the results applying the initial rate, fixed absorbance, and fixed time. And in all cases, we can see we have a very good straight lines, and we can make the measurement of chromium 6 at low concentrations. In this case, we have connected the spectrophotometer and connected a potentiometer in the register output in order to make the analog to digital converter, which the signal is introduced to a week 20, in this period of time when we have made this procedure, this still did not exist, the personal computers. The advantage of this method is you can avoid the use of the manual chronometers, clocks, to read a predefined times. If you have a catalyzed reaction, you can speed the reaction because the catalyzer decrease the energy of activation. And then in this way, the speed of the reaction depends on not only on the products of the reaction, of the reacting components, but you have introduced also the concentration of the catalyst, where X, Y, and Z are the order of the reactions. Since initially you can consider that the concentration of the reacting products are almost constant, then you can introduce these values in this constant here, and finally you can take the logarithm. You can see the logarithm of the speed depends on, is linear in front of the logarithm of the concentration of the catalyst. Quite often, the order of the reaction of the catalyst is 1, then the calibration curve is quite simple because you can represent the speed, or it means the slope in front of the concentration of the catalyst. This has been, for example, applied for the well-known Cerda reaction to make the iodide determination using arsenic 3, colorless arsenic 3, yellow color of cerium 4, giving in colorless arsenic 5 and colorless cerium 3. Then you can control the reaction speed, making the spectrophotometric measurement of the decrease of the cerium 4 color, yellow color. Or you can control the reaction, making the fluorimetric measurements of the cerium 3 produced in the reaction, which is fluorescent. In this way, you will see you can reach ppb's concentration of the catalyzer. A typical example made manually is the reaction of succinimide dioxime autooxidation. I mean, succinimide is oxidized by dissolved oxygen in the solvent using manganese as catalyst, providing a blue or yellow products. The only interference with the reaction is the palladium, which usually is not present in different kind of samples. Here you can see again the application of this kinetic catalytic determination of manganese using the initial rate, fixed time, or fixed absorbance. You can see has a good reproducibility, both reading the yellow product or the blue color. It has been applied to determine manganese in different kinds of regions. For example, it can be determine iron in perchloric acid. The reported maximum quantity was this percentage, and we have found, applying this method, the true value in the region. Have been applied also to more salt, giving also good results, and also to EDTA products, which was not reported because the iron content in region is very, very low. Another way to apply the kinetic methods is using the induction period of the reaction. For example, this has been applied to making the fluorimetric determination of selenium using methylene blue. When you have no catalyzer, you can see that the reaction begins after an induction period. This period is decreased in the presence of the catalyst. Then the time of induction may be represented with this equation with a very good linearity, and the fluorescence is made to these wavelengths. You have not very sensitive, but not good for sometimes, with a limit of determination of 0.06 milligram per liter with good reproducibility. One interesting contribution was we were able to find the equation when the catalytic reaction is produced in presence of activator on inhibitors. The equation is this one. For example, the speed of the reaction with only the catalyzer is a linear equation without the activator or the inhibitor. But the slope of this equation changes in the presence of the activator of the inhibitor. And then this equation is transformed in this, where the slope has the influence of the presence of the activator or inhibitor. For example, the oxidation of thiosulfate by hydrogen peroxide, this reaction is catalyzed by vanadium-5, but wolframium-6 has a behavior as an activator. Without wolframium-6, you have this slope, and with the presence of different quantities of wolframium-6, you can see that the slope is decreasing. The equation that you have to solve is the speed depends of these variables. You can find A, B, and C, these parameters, making minimize the residual square function that depends on the factors, and optimizing the difference, minimizing the difference of the speed experimental minus the calculated. You are changing this parameter, then the calculated value, they can find the minimum using the Gauss-Newton method or the simplex method. Another example is that an inhibitor we have used lead-2 as activator. Manganese-2 is a catalyzer of the oxidation of tyrol, organic compound, by hydrogen peroxide. What we do is we make the reaction using a reflectance probe with a burette. We take different quantities of lead, and then we can build this calibration curve where you can see the activator, the influence of the activator on the slope of the catalyzed reaction by manganese-2. Then we can determine both components, for example, manganese in the 1 to 5 nanogram per liter range, and lead as activator in 200 to 800 nanograms per liter. Sometimes we may apply the thermometric measurements to control the reaction speed. One example is when you are making a titration of a base with perchloric acid in the presence of water and acetic anhydride. Then, where you have the base, you are making the titration with perchloric acid, and you have a constant temperature. When you have the first excess of perchloric acid, then it catalyzes the reaction between water and acetic anhydride, and you have a very sudden increase of the temperature. A very high increase of the temperature, you can use a beaker introducing another wine. You can use a Beckman thermometer in order to see a sudden increase of the temperature when you have arrived to the end of the titration. I will provide now several kinetic methods, so several examples. Can be applied manually. This means you need a clock to control the time. It was used in the former times of kinetic methods. Later, with the use of the computers, you can perform automatic kinetic methods. Has the advantage you are using the clock of the computer, and this provides a very good reproducibility. And you can improve the automation of this method using different kinds of flow techniques. For example, sequential injection analysis, flow injection analysis, multi-syringe flow injection analysis, multi-pumping system, chip-based systems. An automatic flow kinetic catalytic method is based on the use of computer, the control, the addition of the sample, the different regions. This can be peristaltic pump, multi-syringe or monosyringe, or solenoid pumps. They are mixed in a thermostatic chamber, and the result of the reaction can be controlled by spectrophotometric, fluorimetric, chemiluminescence, thermometric methods, using initial rate, fixed method, multi-component analysis, etc., etc. The advantage of this automatic method is all the system is reacting in a very closed system. Then you cannot have losses of components. It is protected from external contribution from the environment with a very high reproducibility. This process can be used, for example, in the photometric degradation of some pesticides. You can introduce the solution of the pesticide, is irradiated with a UV lamp, then from time to time, controlled by the computer, you can take a small portion of the sample and send this to the detector. The great advantage with using the flow system is you pick very small quantities of sample of the order of microliters. This do not affect the big quantity of the solution contained in the beaker. Then we have here calculated the change of the degradation of dicamba and 2,4-D in ultra pure water in drink waters. A very interesting system to control the kinetic methods using thermometric measurements. Thermometric measurements, you are using Whiston bridge. Then you can connect an amplifier and you can power the Whiston bridge with a stable power source. Then you can place the solution in a beaker that is placed in a dewar flask. Inside of the beaker, you have a thermistor. You manually can add the catalyst to the sample solution and stir the solution. And then you can connect the amplifier to a personal computer. If you have an amplifier, you can measure change of temperature as low as 0.001 centigrade degrees. It means very low temperature change. Here, for example, you have an example using a specific thermometric determination of trace vanadium in steel based on its catalytic effect of the oxidation of gallic acid with bromate. In this case, we have a bridge placed inside dewar, surrounded by porous pan to have a very good isolation from the external temperature. We use a synchronous motor from a washing machine. The way we steer the system, we have a thermistor connected to the Whiston bridge, and here we can manually or using a flow system introduce the catalyst, the sample, in fact. It will be, for example, could be the arsenic plus cerium for to make the measurements. In this case, we have used inside the beaker gallic acid and bromate, and then when we add the vanadium, we have different slopes. When we represent temperature in front time, we are using the initial rate method, where the slope depends on the concentration of the catalyst. In this case, the catalyst can be determined as low as the order of microgram per liter. Without catalyst, we can see there is no reaction. One of the advantages of the thermometric methods is that they are blind reactions. It means you can apply the methods in colored samples, and indeed you have suspended solids. This means you cannot use fluorimetric or spectrophotometric methods. The other advantage of the catalytic thermometric methods is they're usually quite selective. Some of them are specific and allows to determine very, very small concentrations of the catalyst. You are using a flow method, for example, flow injection analysis method or multi-stream flow injection method. What you can do is when you have added the catalyst, the reaction begins to increase, you stop here. And if you have reached the equilibrium, you have a stable value of the signal. But if you have a catalyst, you can see that the signal is not constant, but increase depending on the concentration of the catalyst. Then you can represent the initial rate method in order to make the determination of the catalyst. Here you have, for example, the determination of molybdenum blue that catalyze the reaction of between this organic compound and hydrogen peroxide. You can see that depending on the concentration of the molybdenum blue, how is changing the slope using the stop flow method. In this case, we have had the help of a device made using a 3D printer. In this way, with a multi-cyclic flow system, we can add the different kind of reagent, and you can add also the catalyst. All are mixed here, and using optical fiber, you can illuminate here and send the radiation to the detector. In this case was a spectrophotometric method and allow to make the determination of molybdenum 6 with a very low concentration range, with a detection limit of 1.2 micrograms per liter, with a quite high sample throughput of 20 injections per hour. This has been successfully applied to determination of molybdenum in water sample and in pharmaceutical products. Another detection system you can use is applying a chemiluminescence method. In this case, we have applied this to an enzymatic method using glucose oxidase. Glucose, in the presence of glucose oxidase, is transformed to gluconic acid and hydrogen peroxide. And this hydrogen peroxide is able to oxidize luminol, providing water, and this reaction is catalyzed by cobalt-2. The luminol is transformed to the 3-amino phthalate. Then the system is quite simple. You are using a reaching valve. Here you have immobilized the glucose oxidized. Then you can inject here the sample. Here is produced hydrogen peroxide. This is oxidized by in the presence of the catalyst, and producing the oxidation of the luminol, and the product is sent to a flow cell, is this one. It has a spiral placed in front of a photomultiplier. And this allows to determine glucose indeed in non-glucose containing drinks. It means you can determine very, very low determination of sugar. For example, 8.6 per 10 minus mole per liter. Also, the reaction could be applied using hydrogen peroxide and luminol can be catalyzed, and in this way determine cobalt to at this very, very, very low detection limit. The chemiluminescence may be applied also, for example, to determine some compounds that can provide gaseous components. For example, sulfide can be transformed to sulfuric acid, adding an acid. This is sent to a gas diffusion cell where a Teflon tape is made between two metacrylate blocks. The hydrogen sulfide may cross the Teflon, and this is accepted and sent to a chemiluminescent flow cell. This produces, the sulfide provide is a catalyst of the reaction between luminol and hydrogen peroxide. In this way, you have a detection limit of 0.003 milligrams per liter of sulfide with this linear range and this sample throughput, and with a very good precision. This has been used to determine sulfide in leachates and various types of water samples. One very known reaction I have already mentioned at the beginning is the Sandel-Koftal reaction, used to make the determination of iodide, which is a catalyst of this reaction. This
sorry
reaction,
to interrupt you, sir. Kindly, sorry to interrupt you. Kindly, the presentation time has been exceeded, so kindly please wind up.
Okay, then I will finish.
Thank you.